Okay, okay.
Can you record?
Oh, it is.
Okay, perfect. And then I move. Okay, the microphone is there, right?
Yeah.
Okay. Thank you so much for being here today again. Today we will talk about the other questions, and specifically our question is which are main drivers affecting biodiversity and the relationship with ecosystem functioning. This part of the course is longer, and then we will split this part in two different parts, different hours. And then after 1 hour, we will stop, and then June 16, we will start again with the same topic. Today, we will talk about the regional changes of ocean and physics and chemistry. We will talk about how biodiversity responds to different kind of drivers. And then we will try to understand which are mechanisms affecting biodiversity. You need to recall that the 95% of animals and organisms, marine organisms are ectotherms, and then they adapt their body temperature to the external conditions. And then they don't have specific control of body temperature, and then spend energy to try to adapt. They don't spend energy to adapt the body temperature to external condition like other organisms, like mammals, for example. Another important information is that they are with indeterminate growth. And then this means that they start when they have the possibility to allocate energy to reproduction, they immediately allocate energy to reproduction, and they continue to allocate energy to reproduction for the whole lifespan. Instead, when we talk about determinate organisms, these like us, like mammals, like some birds, we have a different behavior, and then we allocate energy, we grow up to a specific size. After that, we start to allocate energy to reproduction, but we stop the growth. And then these different behaviors are important repercussions in terms of energy budget, in terms of the mechanisms how to respond to temperature variability at sea. And then we try to understand which are main mechanisms how to marine biodiversity are able to respond to temperature variability. And then we recall that the first and most important factor affecting the biodiversity is the increase in temperature. You know that the marine ecosystems have absorbed approximately 93% of the excess heat generated by greenhouse effect. This means that although the water has an internal inertia to respond to the heat absorption. However, the water mass is able to slowly respond to the heat absorption. And this means that we have a slow increasing temperature respect to the higher masses in terrestrial habitats, but we have a slow increasing of temperature. But this energy contained in the water masses is able to explode, to modify, to change the dynamics of the relationship between water and air, and then we have different repercussions in terms of marine heat waves or just cyclones, storms, and so on. We have different effects of increasing temperature. Melting ice, for example, is just one effect. This is able to increase the sea level rise. We have a different kind of effects in terms of in the last century, in the last decades, or in the last years. We had a sharp increase of temperature of global surface marine water masses. And then, for example, the last was these last 5-6 years, we had just this sharp increase with this spike in 2023. But it's not true, because 2024 and it was also higher than 2023, and 2025 is just expected to be higher than 2023 and 2024. Usually, the increasing of temperature is predicted by scenarios, and in our models we use a different kind of scenarios. We can use the business as usual scenarios, and then this means that we assume that we don't change our behavior in terms of emissions of greenhouse emissions, or we can try to understand which is the role of different different policies around the world in every country, and then lowering the emissions of the CO2. And then we have different scenarios. For example, we use the RCP 8.6 or just the 2.6. These are different scenarios that we include in our models, in the DB models, for example, just to simulate the different kind of increasing temperature in the future, because we have one objective of our work, our scientific approaches, is just to predict what will happen in the future to our biodiversity, but we have a different kind, we don't know which will be actually the future trends, and then we use different scenarios just to guess out what will happen in the future under different behaviors of these human societies. We have just the last time I just showed you that if we increase the CO2 in the atmosphere, we have an amount of CO2 increasing absorbed in the water masses, and this create some issues to carbonate equilibrium. And then you recall that that point is really important. That point of pH of 7.8 is really crucial, because below 7.8 calcifiers organisms and then shelled organisms, all possible organisms with carbonate structures are not able to fix carbonate, and then they have different kind of repercussions in terms of fitness, because which is the role of valves, of shells, are different roles. But the first role, for example, is just to avoid or to limit the predation. One crab, when one crab attack just a mussel or just one oyster, usually crabs spend a lot of time just to crash, to break the shells. You need to when we have, and then at these times we measured. There are a lot of papers measuring the time of the breaking time of shells in mussels, in oysters, and other organisms, in general bivalves, at pH, at normal pH, 8.2, 8.1. But the situation is totally different, because the breaking time changes when the pH is lower. If you have bivalves adapted or just living a pH lower than 8, the shells are softer. And then the breaking time of crabs to predate valves and organisms are short. And these have a repercussion, cascading repercussion along the food webs, because the time in ecology, recall this, remember this, is really important. The time is just a variable, just something that we need to understand how to manage it, because the structure of the food webs is based on the structure per se, but also on the different times of exploitation of each organism, other organisms, and then the time is really important. Other effects that I just to recall what we said last time, the oxygenation, the diminishing, the reduction of oxygen level at local level, and then this is a really new driver for our biodiversity. You can have different kinds of drivers of the oxygenation. You can have local drivers, for example, because at a local level, contamination can push the lowering of oxygen level, but you can have also a global effect of just regional effect of the oxygenation due to the increase in temperature and other global factors. And then the oxygenation and then the reduction of oxygen level at local level is maybe one among the worst factor affecting biodiversity. And then we need to understand how the oxygenation has effects on our individual response. Actually, as we said, we will see later. The oxygenation is always combined with increasing temperature. And then we have at least two factors: the increasing temperature and the reduction of oxygenation. And then biodiversity have to respond to at least two multiple or two different stressors: the oxygenation and increasing temperature. And this is the best situation when we have only two stressors acting together. Acidification is possible when you go to the vents and you have acidification. Very often in the Mediterranean, you have also a sort of deoxygenation. And then you need to imagine that in that place we have increasing temperature, deoxygenation, and acidification. And we have in this case just three factors working together. Acidification, I wrote here as acidification, deoxygenation, and increasing temperature together pose major threats to marine organisms, because they have effects or at different levels of the energy budget. On the external part, acidification, shells and valve. Internal part, the lowering effects of the reduced effects of oxygen has effect on the energy budget. And then there is a really dramatic, in my opinion, situation. Another important effects that we just talked about last time is marine heat waves and storms. These are another important factors that biodiversity should or have to cope with. And then we have a different, in this diagram, I reported the different kind of factors interacting among them. What is really important is that this compound, this word, compound effect. The compound effect is just when different kind of factors interact together to have just to affect biodiversity. And then when we have a different kind of drivers acting all together, this produces a compound effect. Very often the compound effect is really not predictable. And then our ability to predict the effect of compound of all possible multiple stressors all together is really low. We have what will happen years before. And then in 2003 and 2004, we had these spikes of increasing temperature, and we had some different kind of mass mortalities. For example, in the DEB model is possible, or in some different species distribution models, mechanistic species distribution model, we will them later, is possible to introduce a series of increasing variance of temperature. And this is really important from a scientific point of view, because you introduce realism, a realistic scheme of thermal variability at local level, and is actually what organisms experience, because organisms staying in this place, they experience just this large variability. And then another type of experiment is, for example, include different kind of thermal variants, and then you play with variants, not with values per se, with the magnitude, and then you try to understand which is the role of variance respect to the magnitude, the intensity of the effect. For example, here we measured, if you are familiar with the DEB model, maybe some of you, the PM, the somatic maintenance of these animals. We just simulated some, I don't remember, recall just 10 years ago, bivalves. We simulate the introduction of the heat wave in the lifespan of different kind of times, and you have a lifespan of 3 years or 5 years, for example. You can image to introduce a different specific time series of heat spikes, of heat waves, and then to understand which is the repercussions along the lifespan of this specific increasing thermal variance in the lifespan. And for example, we observed that we had in those periods an increasing amount of energy spent for somatic maintenance, and this has an effect in terms of body size and the amount of eggs, for example. Which is the situation in China. China is like other regional places in the world. Other regions are subjected to increasing temperature or just in general to climate change impacts. In this case, for example, in this paper, you know, because it's from here, is possible to, they simulated the effect of climate change or increasing temperature in the water masses along the China coasts. Recall that you have, in China, you have 2,500 kilometers of coastline, right?
Yeah, like 10,000.
10,000? No, but in terms of latitudes are 30 degrees, more or less, almost. In Mediterranean, we have only 9 degrees. And then you need to understand that you have these large coastlines, and in every coastline, in every place, you have a different regional situation. In the Med, is not so easy to have different patches of response. When we have an increase in temperature event, like in this period that we have 35 degrees, we have all Mediterranean involved in the increase in temperature. Here, no. You have, for example, the Shandong in the Yellow Sea area. They say that you have a quicker increase in temperature respect to other areas, and then northern parts seem to be more affected by climate change in respect to the southern part. This is pretty true also in the Europe, in the northern part of the Europe, Baltic Sea, Northern Sea, channel between UK and France. We have different behavior of water masses increasing temperature respect to the Mediterranean. But which are the effects of climate change of organisms? Are of two different types: indirect or direct effect. for example, we can have an increase in temperature or just an effect of climate change, increase in temperature of the oxygenation on that is not so hard to induce mass mortality in the target organism, but we can have an effect through diseases, for example. And then increasing the frequency of disease can have an effect in terms of mortality, mass mortality. This is an indirect effect because it's just as an effect on the metabolism of target of our bivalves. For example, in scallop, chlamys, nobilis, but the effect is through disease. We have or you have a different kind of example. This paper just really in 2021. This, for example, is a 2025 is a new because there are always they measured always the effect through disease or just through bacteria or just through viruses on bivalves in aquaculture and so on. We have another examples of indirect effects in China seas. This fish killing bloom in the Beibu Gulf. I don't know where is the Beibu Gulf. Southern, okay, and then due to the dinoflagellate, and then you have not a direct effect on scallop, but you have the effect on other components of biotic components of the ecosystems that by cascading effect affect the scallops, and this is really, really important. In the Mediterranean, in 2017, Garabou et al. With a couple of papers, one on trends, one in ecology letters and another in global change biology, they measured different kinds of effects in the Mediterranean. And then we have the mass mortalities at -30, -50 meters, and then on the benthos, on the benthic habitats, on the coralligenous habitats. They measured the mass mortalities. In this case, this is a direct effect, but because you know which is the behavior of temperature at deeper layers. Usually, organisms living on the bottom after 20 meters, more or less, so 10, 20 meters deep, usually they experience a really stable environment, thermal environment. And this is common along in every parts on all global oceans. In the Mediterranean, we have a specific stratification of temperature, and usually lower than 20 meters, like I guess here. We have just a stable, really stable temperature. Instead, they measured really really important events of increasing temperature just at 20, 30, 40 and 50 meters, and this created the conditions for a mass mortality, because these organisms are adapted to stable environment, and then when you increase the temperature of only some degrees, they die. Is not true. The same is not the same, for example, in the intertidal habitats, because intertidal habitats are really variable, and then organisms in the intertidal habitats usually experience really variable temperature, and then the effect of marine heat waves, so just heat waves, atmospheric terrestrial heat waves, should be really stronger respect to what happen in other parts of the marine ecosystems. We have also this paper, just in this case, we can have, they measured a cascading effect. And then you have, in this case, you can have an effect on one component of the food web. And by cascade, you can have a cascading effect on the other components of the food web. And this is really interesting, or just really not so good, but really interesting from a scientific point of view, because you have a chain of effects transmitting along the food web. And due to trophic and different kind of alteration. The alteration in this case, you have just an issue at one level, and the transmission is a trophic transmission along the food web. And in this case, mass fish kills may have cascading impacts on ecosystem functioning by causing shifts in community structure and a decrease in biodiversity, which can reduce the ecological functioning and the economic stability of marine-dependent regions. This study is from the Red Sea, but there are a lot of different kind of examples around the world now. Okay. How is it possible to identify mechanisms of effects of climate change on our biodiversity? The first point that usually temperature in hectotherms affects is clearly the metabolic rates of one organ. And in this case, we use the dynamic energy budget model just to simulate the effects of metabolic rates. In this case, we have this nice diagram showing which are different life stages affected by climate change, increase in temperature. Starting what is the point of to start from adults. Adults can have usually effects or receive negative effects of increasing temperature just on the reproductive processes, metabolic rates, growth rates, and then all possible performance traits. And then size, we have an effect on size, we have an effect, a consequent effect on reproductive production, and we have a direct effect on survival rate. And then these three performance traits are usually affected. And by cascade, we have different effects from a biological point of view and different effects from an ecological point of view, but we will see it later. Just an example, Carlos Duarte, which is a really important scientist in the world, has just written this paper in 2007, just 20 years ago, more or less. And he simulated the effect of temperature on PLD, the plankton larval duration. And then we have evidence that planktonic larval duration in marine species decline exponentially with increasing temperature. This is predicted by metabolic theories, both that the metabolic theory of ecology by Brown and Gilloley 2001, 2004, and by the Bas-Koeman in the dynamic energy budget model theory. And then what he says a really simple thing. If you have an increasing of temperature, the metabolic rates of larvae is quicker, and then they become adults before. This is important for example, the connectivity among different places, because if instead the plant, you know that most organisms at sea, they usually use the water mosses during the plankton larva stage just to move from one place to another place. If you increase the metabolism, if you increase the period in the plankton is shorter, the distance, clearly, the distance that plankton or just larvae are able to do is shorter. And then these have direct effects in the on the distribution of planktonic stages at the regional level, and then instead to reach a place at 50 kilometers, they reach a place, a site at 20 kilometers. From a connectivity point or level, from different kind of biological and ecological level, this is really important. But what, and you just see saw before this graph, this which is really important in my opinion. What is really important is this model of this behavior of growing by most organisms on this planet. This is the von Bertalanffy growth curve. And then we know that if you put time on the x-axis and you measure the growth rate on the y-axis, the curve is usually this type of curve. Okay, we know from the metabolic energy, the metabolic theory of different kind of metabolic theories, that if you decrease the amount of energy that one organism is able to manage, or because they don't have access to food, and then we have reduced energy through food, or they are sick, they are not able to manage too much energy, the effect is the reduction of body size. Okay, the body size is a really important variable which is usually affected by climate change. When you increase temperature, we showed with the different kind, there is scientific evidence that usually organisms are smaller. If you also try to these changes, these pattern is changes between northern latitudes, southern latitudes is not important, but we have a direct effect through this kind of curve model on the body size of our organisms. And if you have a reduction of body size, you have a different kind of repercussion. This means, for example, when we simulate in the B model, that at the same age, what I mean? I mean that at the same age, we have a smaller body size respect to another body size or another organism which is larger. Which are the effects of this? The effect is immediate on the amount of the reproductive output. There is a link between the body size and the reproductive output, the number of eggs produced per gram of body size, and in this case, Bas Koyman has used this theory just to feed the dynamic energy budget theory. And then if you have larger body size, you have larger amount of eggs. If you have smaller body size, you have a smaller amount of eggs. If you have also an increase in temperature, you have a shorter time to stay in the plankton, you have a secondary effect. You have less eggs that cover shorter distance. And then if you can understand that we have biological and the ecological effects interacting together, because the temperature affects, an increase in temperature is able to affect other drivers. In general, multiple stressor affect the amount of energy. The amount of energy affect the body size. The body size affect the eggs. Indirectly, the increase in temperature affect the planktonic duration time in the plankton of the larvae, and then you cover less distance, shorter distance respect to the normal conditions. And then you have a less number, a lower number of eggs covering a shorter distance. And then instead to reach, I don't know, in China, but in the Mediterranean, instead to go from Palermo, from my home to Messina, they just arrive and recruit just in the middle. And in the middle, for example, there are no hard substrates. If you don't have hard substrates, for many organisms, they are not able to recruit at local level, and these larvae die. You lose this potential of biodiversity. This is a sort of cascading effect that we are observing at sea, and all possible effects starts from the reduction of body size. Okay? Apart from the von Bertalanffy curve and the relationship between size and gonadic mass, I recall also last year, I just invited you to read this science paper, Barnesh et al. 2018, because it's really important, because they measured this relationship in 500 species, organisms, marine organisms. Another important theory is about the response of the relationship between environmental factors and metabolic rates, of just a different kind of rates or different kind of performance. You know that most of all organisms or ectotherms on this planet usually have this type of response along if you change the local conditions, local factors. This is the Inna Sokolova model, which is emerged from the Hans Otto Portner model, which is that model, this model. And why these models are important? They showed that if you put all together different kind of factors, the performance reduce. And then when we talk about before about compound events, when we talk about different factors interacting all together, the effects at the biological level is more or less this. This means that you don't change the shape of the curve. You reduce the magnitude of performance at the same shape. The shape of the curve is species specific, and then you can have different kind of curve as a function of each species. And this is really important because we will see that is every species has a different kind of response at different conditions, at different temperature, at different salinity, at different pH, for example, and these compose a typical response, community response. Okay, before to go. Yes, because before to start with the, we can stop now here, and then next time we will continue. We will continue with the second part. Okay. If you have some question, here we are.
Any question?
I have some question.
Union.
The first question is your study for crab and oyster. Because you show the low pH condition and oyster is low and easy to catch for the crab. And I wonder, in the different condition, I mean the low pH condition have another effect on the predator on the crab. For example, because for example the low pH condition, maybe the crab is not comfortable. Yes, they may be hungry or eat more.
You are really right, and this is a limit of our experiments. But actually, we put also crabs in for the same time, the same condition of pH. And then we didn't have effect significant on the behavior, on the response of crab. Crab were always active and aggressive in breaking shells of oysters. Okay, and then I think there is a latent effect, with a different effect on shells and on the crab behavior. And then this type of experiments are long for the time sufficient to modify the shells, but we don't never did experiments with the time sufficient to modify also the behavior of
short term. And I have another question about the food. In Sicily, I mean the hourly temperature. Yes, the marine heat wave. And because in my thought, I think dynamic energy budget model can show the global warming effects. I mean, a long-term effects, but you show that hourly temperature. And that's yes. Yeah, I just wonder if we can use hourly temperature data and to predict to combine with the model to predict the energy loss or the structural maintenance. That's it makes sense.
We all possible our models in a paper with Brian Helmut. In a paper with Brian Helmut, we showed that if you use the frequency of 1 day, and then if you use an average of temperature per day, you lose the accuracy and precision of the DB model. And then we used a temperature value per day, two temperature values per day, 12 and 12 hours, 6, 6, 6, 6, and then 4 temperature, and then later 1 hour. Okay, and then we simulate the same DB model with different frequency of temperature, and what we observed that the effect on the body size after 3 years was really large. Okay, and then my advice, why we use the 1 hour thermologgers, that's clear. This is from local thermologgers. If you want to simulate the DB model of salmon at a global level, you don't have 1 hour time series. And then is a sort of trade-off. When you have data from buoys, oceanographic buoys of just thermologgers, we have in the Mediterranean, I think you have oceanographic buoys here, measuring every hour.
Yeah.
You can use this time series for local or regional. When your question about the effects of climate change of organisms is at the global level, your compromise is just to move to other frequencies and not one. But the effect to use 1 hour is large.
So that means if we have high resolution temperature data, that means hourly data, we can use to predict the thermal sensitivity.
Yes. Yes.
Oh, yes.
Here, what we did, I used the before the DB model with this the temperature series without spikes. Later, I ran the model again with 4 years with spike. And then the results was 40 plus 40, 70% of metabolic maintenance energy spent more. And this had a large effect in terms of body size and amount of this. In this case, we used also the simulation with one day. You lose the accuracy. Yeah, you lose the accuracy, and then the amount of energy was not so detailed, but it was not so detailed actually. Another one way just that you can is resolve when you have the day temperature, you can use 24 hours day temperature. I mean, you repeat 24 hours the same temperature. And you have the 1 hour. Oh, it's easy. We have the script. We have script just to run. It is in an hour. If you have 1 week, which is the frequency of your temperature? Months. Okay. If you have just 1 day, you repeat 24 hours the same temperature, and then is it possible just to try to understand how it works. Another question, guys and girls? Huh?
Yeah,
Yes. Okay.
So if now any more questions, let's start the Garuda again.
Thank you so much. Oh, see you next time with the second part.